we are discussing boundary value problems for flexure. We are following stress function approaches. So, in the last class what we have discussed is the different types of stress function possible, for instance quadratic and the fourth order stress function, and these stress functions for a different it has different constants. So, by tweaking or by efficiently managing these constants or in explicit way, that if some constants we take non-zero, then we can create the different stress state in the body. So, at the end of the last class what we have discussed is the how to obtain a solution of a beam which is having a point load through the theory of elasticity approach. So, in this beam problem, if you look carefully, that we are using a 2D cantilever beam loaded at free end, and this free end the resultant force is P, and we are following plane stress condition because we take C is much greater than or 2C is essentially much greater than T. So, now the boundary conditions, as we have discussed in the last class, boundary condition, since we are following stress function based approach, the boundary condition has to be in terms of stresses. So, these are the boundary conditions, we need to use it. Now, here we have done it with a simple stress function which is motivated from our knowledge of strength of material. If you remember that stress function, which is pi is we have taken as phi we have taken as a x y. So, this a x y is motivated from the our knowledge in the bending moment or the sigma flexure formula that we have learned, sigma equals to m y by I. So, this leads to sorry, this is not pi, this is essentially the sigma. So, sigma xx, which is essentially del square phi by del y square. So, this is the motivation, if we remember. Now, this motivation is through the strength of material approach that we have following we have known till date. Now, this can be also, if we in some problem where the strength of material approach we do not know the solution by strength of material approach. So, what should be the stress function and what can I assume as a stress function? This can also be done. So, let us see this problem. If we do not want to use our concept of strength of materials, how this problem can be solved. So, for instance, if you remember in the last class that we were discussing about a quadratic polynomial phi 2 of bxy, which represents the pure shear case, and there is a phi 4, the fourth order polynomial, which is represents this straight state. So, which is essentially this sigma xx is of this form, and sigma yy is 0, and sigma xy is a quadratic form, or it represents a parabola. So, if you have remembered this thing, we have discussed it in the last class. So, now the basic idea is we know these stress functions and which we have found out. Now, if we superpose or superimpose these two stress function and describe that is our phi, then also it satisfies the biharmonic equations. For instance, if I add phi 2 and phi 4 and then say that phi 2 and phi 4 is my phi, then this phi is satisfying this biharmonic equation. So, if you remember carefully, this biharmonic harmonic equation is essentially a linear differential equation. So, the linearity property allows us to superimpose the two different phi, and since the individual phi, this phi 2 satisfies by harmonic equation, this phi 4 also satisfies by harmonic equations, and then sum of these two phi 2 and phi 4 will also satisfy the biharmonic equation. This is the property of the linearity property. Now, if we use this is as phi, which will leads to my phi is bxy and d by 6xy cube. Now, which leads to two constant b and d. So, earlier if we remember that we were only doing with phi, or the we had only one constant, and which is, if you remember, which is a by 6 xy cube, which was our phi. Now, this phi and this phi, what is the difference is that we just add another constant or another term in that phi, and which is coming from the pure shear expression of the quadratic stress function. Now, let us see if we use this how it will look like. So, this is my phi, and so my stresses will be sigma xx will be dxy, sigma yy will be 0. See, these are very similar to the previous way of solving this thing, and the only difference lies in the sigma xy, where the b minus b term is added with this term. So, now if you carefully look, this already satisfies the forces, that is sigma yy at sigma yy at y equals to plus minus c equals to 0. This already satisfies this phi. So, which is sigma yy is essentially 0. So, now by the other thing, that sigma xy, that is, there is no shearing force at the top and bottom layer, bottom fiber of the beam. So, this becomes gives us d is essentially minus 2 by c square. So, how if this you substitute y equals to c and then equate it to 0. Now, the third condition, that is minus c2 plus c minus of sigma xy dy, which is equals to resultant force P. Now, this if we write in terms of B, because we substitute D here, and which is 2b by c square, and then plus, and then use this, put it back in this expression and then integrate it, we find B is this. Now, once B is this, we can also calculate D from this expression, and then finally invoking the moment of inertia, which is 2/3 c cube, 2/3 c cube, then we can write D is this. Now, if you look the stresses in terms of these constants, then stresses is this, sigma yy is 0 and sigma xy is 0, which is pretty similar with the previous case. So, that means there are several ways to find out the solution of this problem within the stress function approach. So, you can even choose the stress function intuitively from your knowledge, or some superposition of the two stress function depending on the stresses that will occur in the body. So, this is another approach we have seen here. So, now, so what we have discussed in the last class also, that this sigma xx, sigma yy and sigma xy is very much same with the our knowledge of stresses for the beam. So, which we have approached via strength of material approach, and where we have considered as a one-dimensional beam with a cross section and all those things. But here it is a truly two-dimensional approach, whereby which with certain modification of the stress functions we got this thing, which is similar to the beam of the stress strength of material. Now, our objective here now is to find out the displacements. What will be the displacements if we have these stresses? So now and finding out displacements is very easy, because you know the stresses very well, and if you know the stresses, then you have to invoke the material behavior, which will essentially here the isotropic Hookes law here, isotropic material we are considering, so which contains only Poisson's ratio and Young's modulus. So epsilon xx we know, which is del u del x, and so since sigma yy is 0, so that is sigma xx by E. So we know that from our Hookes law knowledge, and sigma xx also we know, which is minus pxy by EI. So now if we solve this differential equation, then we get a form of u. So which is minus px square y by 2 ei plus fy. You see this integration is with respect to x, and remember u is function of x and y, and v is also function of x and y. So both of these are function of x, y. So the integration constant, when you are differentiating with respect to x, then this will be a function of y. Similarly, epsilon yy which is del v del y, which is since sigma yy is 0, so sigma yy by E term cancels, so minus nu is the Poisson's ratio sigma xx by E, and which is nu pxy by Ey. Now again, by integrating this, I can get the v, where the integration constant will be a function of x. Now if we substitute u and v in the shear strain, which is gamma xy is del u del y plus del v del x, which is sigma xy by g, the shear modulus, the relation between shear modulus and Young's modulus and Poisson's ratios we know, which is E by 2 into 1 plus nu. So this sigma xy also we know from our previous calculation, and if we substitute this sigma xy, then the right hand side will be looks like this. Now if we substitute this u and v, that means del u del y and del u del v del x here, so we get a expression, or we get a equation of this form. Now look carefully, these some terms in these equations are purely x, some terms in these equations are purely y, and some terms are constant. For instance, this term is a constant term, and this term is essentially purely a x dependent term, and this is a y dependent term. This is also a x dependent term, and this is y dependent term. So now if we write it in a proper way, so let us see how these things is. So these all these two terms are x dependent, which I am saying fx, and this is a function of x, and this is y, which is a function of y gy, and this is a constant which is k. Now you see, if I write it here, that f of x function of x plus function of y, function of y gy equals to some constant k. So now this is a function of x, this is a function of y, and this is constant. Now if it has to satisfy for all x y, then each of these has to be constant, because otherwise it will not match with the k. So let us assume that function of k, function of x is constant, which is d, another constant, and function of y, which is e. Now if we assume that function of x is z, function of x is d, then this term will be constant. Now if this represents this. Now again, this is a differential equation. Now this differential equation, we can, if we integrate it, then we get this gx, which is a one variable function of x. So this becomes this. Now similarly, gy, which is e, essentially we can write this as a differential equation. Now this differential equation, again if we integrate, so we get fy, which is of this. Now finally, my u and v, which I have obtained from the previous slides, can be written in this form. So this u and v, just we plugged gx and Fy in the uv. So, here you see that there are 4 constants. One is E and Q and then D and P. These 4 constants we need to find out. Now, from these constants, from where we will find it out? The first we need to realize one thing, that D plus E equals to K. This is another equation we have. So, these equation we should not forget, because there are 4 constants. So, we need to have a 4 equation at least. So, to find out the complete displacements. So, D plus E equals to K. So, now that reduces one of our constants. So, which is E or D I can express in terms of the other. So, now we need 3 more constant, 3 more equations. So, what are those equations? Now, this will come from the rigid body modes, to prevent the rigid body modes. So, in a 2-dimensional problem, what are the rigid body modes we need to address? For instance, in a 2-dimensional problem, we have 3 such things, that is x displacement, y displacement and rotation about the xy plane. So, these 3 boundary conditions will give us the 3 required constant to find out the displacements properly. Let us see. So, now here now see, this is our constants which we are discussing in this. So, E and Q. So, this is my one equation that we need to use. So, first constant that we want to first boundary condition that we want to use is that at this point that u at x equals to L and y equals to 0, v at x equals to L and y equals to 0 is 0. That means, this point is a fixed point. Okay. So, this point, if I use this boundary condition, straightway from the first equation I can say this q term goes to 0. Right. Now, if I put this boundary condition here, then I can get P in terms of D. Right. So, now the deflection curve, which all of you have familiar with, or the sometimes we also call it elastic equation of an elastic line or something like that. So, this curve essentially, this line which is at y equals to 0, we can find out which is v. If I put y, then p x s cube c 6 e I minus p L cube by 6 e I. So, and in terms of d. So, because again we did not solve this proper yet. So, P is in terms of D. So, that is why constant D remains in the elastic curve. Now, you see, to find out this elastic curve or the deflection curve, we need to find out D. So, what should be the D? Now, finding out D, we can use at this point that our original knowledge of strength of material, or another condition. Let us see how to find out D here. So, let us see for the first case, where if you remember that cantilever beam we are talking about, then this is the, what was this thing at this point, u the v equals to 0 and del v del x equals to 0. Now, what happened in the strength of material case is that v was a function of x only. Right. So, del v del x is 0 at this point, that means slope at this point is 0. But here what is now is the problem is that our v is actually function of x y, because we are considering the body as a 2-dimensional body. Now, this v x y, so that means x equals to L, y equals to 0 we have to consider. So, that x equals to L, y equals to 0, del v del x is 0. So, if we consider those, what does this means? That means at this point any element in the x axis will give me in the or the beam axis is fixed at this point. That means the rotation along the axis of the beam is fixed. So, this actually gives me this. So, now if I use this condition, then I can find out d, which is this. Now, once I find out d, and if you remember, our another condition was d plus e equals to k, which k is essentially minus pc square by 2ig. So, this equation, if we substitute d, then we get the e. Now, once we find out d and e, we can find out the complete solution in terms of all constant known. So, and this solution is, if you look carefully, this is u solution, means along x axis what is the displacement, and this is the v solution. Now, here if you look carefully, that if I put y equals to 0, that means this line is my deflection curve. So, that deflection curve is at y equals to 0, which is this. So, this we obtained, some of you have must have obtained from the in the strength of material or integrating the differential equation, that is beam differential equation, d to the power 4 y by dx to the power 4, or the moment curvature relation. So, now here if you remember what was the displacement for this case, it is PL cube by 3I. So, if you see that if I put x equals to 0 here, so these terms actually gives us the PL cube by 3I, the original strength of material which we have derived from our strength of material knowledge. Now, in addition to that, it also gives you that u v. So, that means through this stress function approach, what we have achieved is that more accurate expression if the beam is two dimensional. If we consider the beam is two dimensional, what will be the displacements in x direction, what will be the displacement in the y direction, we have achieved more. For instance, if the cross sectional displacement, if I want to find out somewhere here the cross section which is at a distance y from something, then this expression will directly give me the cross sectional displacement of the beam. So, this can also be extended for the three-dimensional problem, but again the expression will be very lengthy and complicated thing. So, basic idea is to know the things, the procedure and how we can approach it. So, for this kind of problem. So, this this solution of this displacement, even though it matches, the stresses are matches with the our strength of material case, strength of material knowledge, but we did not have any way to find out those u displacement and v displacement at these points, right, or we did not do that at that time. So, here the theory of elasticity, knowledge of theory of elasticity allows us to analyze it more accurately, or to find out the displacements at the cross sections and in the x direction. Now, another important fact, let us see if we use these displacements and to find out what happens to the stresses in the beam. So, you see this is our displacement u L y, means along the y. So, if we now find out, if we now do some manipulation, then we can see that our u displacement is 0. That means, at x equals to L at this point, x equals to L, and we are checking the what is the variation of the displacement. So, now this is my displacement along this line. Now, the del u del y at x equals to L, which is this. That means the change of this u displacement along the vertical line of the or the fixed end of the beam. So, if we now you see what is this displacement, from where we obtain this displacement? We obtain this displacement that here what we have assumed that del v del x is essentially 0 at this point. So, at this point this del v del x is essentially 0, that we have assumed. So, through this we have obtained these displacements, and now if we see what happens to the vertical fibers. So, that is del u del y at x equals to y is this, and so that means it gives me this line, which is actually if the beam is originally this. So, this gives me this So, this gives me a line. So, a deformation which the tangent to this is this line. So, this tangent is essentially representing this the value, the angle here, this angle is essentially the gamma xy, or the 3p by 4 cg. So, which is essentially how we can obtain, means how the vertical fiber at the fixed end will rotate. So, this rotation can be obtained if you find at x equals to L and y equals to 0, find out this quantity, which is essentially minus p c square by 2 I g, and 2 I g that I can be substituted, that is 2/3 c cube, and if we do that, then this will be my this quantity. Now, sigma x y, if you remember, at this point, which is del or the gamma x y, if you remember, that del u del y plus, that means gamma x y is I am talking about this point. So, del u del y plus del v del x. So, del v del x we have taken 0. So, now del u del y will be my gamma x y. So, del u del y is essentially 3p by 4 c g, and the shear stress is 3p by 4 c minus 3p by 4. So, that is the counter that is the clockwise rotation of the fiber, the vertical fiber at this end. So, this gives me additional information how the shearing effect happen in the beam, and this can be found out at any cross sections. So, so what we have seen here is that if we take the usual strength of material approach and then find out what are the displacements, theory of elasticity approach gives us little more information about the body. Now, instead of that, if you remember that we had u here is a function of x y and v as a function of x y. So, in the earlier case 1, the in plane rotation, how we have prevented in plane rotation? We prevented by introducing the concept, introducing the condition that del v del x at x equals to L, y equals to 0 is 0, that we have invoked. So, which is essentially coming, which is very similar to the strength of material approach for a cantilever beam at the fixed end. But instead of that, if I want to restrict the vertical fiber in the element, a vertical element on the fiber, if I want to restrict, then this condition, that means del u del y at x equals to L and y equals to L, if I fix this, so that means a vertical element of the cross section of the beam is fixed at this point. So earlier we are fixing the horizontal element, now here I am fixing the vertical element. So now if I fix this thing in this beam, then again I can find out the constants, which is essentially the u. So if I take the derivative of u with respect to y, then this term goes off, and this term already we know, which is 0. So this term goes off, so we can find out e, and e is this. Now once we get the e, so e plus d plus e equals to k, which is we know from earlier equation. So we can substitute e and find out d. Now if you see, if I now want to find out the elastic curve, which is in addition to this original elastic curve for this condition, we have one more term here. So you see this term, which is not very similar to the strength of material approach. That means the this L minus x Pc square by 2 Ig L minus x term is additionally creating the displacements. That means that if I change, if I instead of restricting the horizontal behavior or horizontal rotation instead of restricting at this point, if I prevent the element of the vertical line at this point to rotate, then our deflected curve is essentially different. So this actually known as effect of shearing on the deflection. So now we will see what this means. So here actually in the same way, if we have seen this is the deflected curve. Now this deflected curve with this boundary condition, the deflected curve again it rotates in this way. So this again the rotation from this, which is which can be written as the minus 3p by 4 cg. The same way we have derived it for the previous case. Now this extra term is actually can also be written in this form, which is very simple, because if I now substitute the I, then I get this term. So you see the main distinction between two boundary conditions, one of these is so at this point this is the elastic line. At this point, if I want to fix del u del v by del x equals to 0, then I get something which is very similar to the strength of material thing. That means if I want to fix an element at this point in the axis of the beam, then I get a type of deflection, and then if I fix instead of this, if I fix the horizontal element at this point, which is governed by this equation, I get a different deflected curve. That means, and this difference extra thing is this quantity. So this is known as the effect of shearing on the deflection. So clearly this strength of material, this theory of elasticity approach gives us more flexibility, more opportunity to find out or to see how the deformation on a body really happens. So it is in depth we can analyze the structure. For instance, that we could not have U displacement in the strength of materials. We could not find it out, but because theory doesn't allow us to do that. But theory of elasticity gives you the opportunity of how you really can do this, and this is a stress function approach we have discussed. So in a nutshell, what we have learned, we finally summarize it. So what we have learned, we just took one beam, simple cantilever beam, for which the strength of, we have the every knowledge of strength of material, that is what are the stresses, what are the deflected curve, equation of the deflected curve, everything we know, and then we assume some stress function phi, which I have shown you how to do it for two from an intuitive sense, and how to use the different stress patterns to superimpose and to get the required stress functions. So once we solve this stress, once we find out the stress functions will certainly have some constants, and our job is to find out those constants through the stress boundary conditions. So with these stress boundary conditions, we find out the stresses correctly. Now once we get the stresses, what we need to find out? We need to find out displacements. So we invoke the material laws or the constitutive laws into it, and then we find out the displacements from it. So for instance, in this case, the epsilon xx, epsilon yy, and gamma xy, the shear strength. So we know these how these are related with the displacements. So then again we have a differential equation in terms of u, which is first order differential equation. So this first order differential equation we can integrate, then again we have some constants. So those constants again we have to find out from the displacement boundary conditions and the slope boundary conditions. So for the slope boundary condition and displacement boundary condition is essentially to prevent the rigid body motion of the beam, so that it doesn't rotate arbitrarily. Rotate and translate. So this to prevent this rigid body motion, we need to substitute those displacement and slope boundary condition. In the slope boundary condition, we see we can use different slope boundary condition. For instance, we can use this or we can use this. So if we use different boundary condition, naturally we will have a different deflected curve, and so that means we can find out the deflection in u as well as the displacement u and v in the both the direction, because our problem is essentially two-dimensional problem here. So this can be certainly extended to three-dimensional problem, and the stress function will be three-dimensional case for a three-dimensional three variables x, y, z, three variables. So polynomials of three variables we have to consider. So number of constants will obviously increase. Now here we have used the unit thickness, or essentially the thickness is very less compared to the depth of the beam. So this restriction can also be removed, and we can analyze the beam as a three-dimensional problem. But yes, the expression will be much more complicated, and one can surely try those things. So with this I stop here today. So we'll meet in the next class. Thank you.